Hello, welcome to When Building, where we bring insights out of Web3 builders. This podcast is made possible by our sponsor Untitled Labs. Untitled Labs is a Web3 developer community dedicated to push the boundaries of crypto space by supporting the innovation and success of open source projects. Hello, welcome to When Building podcast. This is about zero knowledge proof hardware acceleration. While we all care about how ZK makes our life better, the tools that makes it easier is also crucial. In the past podcast, we talked about proving systems that might evolve a lot, which is something make proof generation more efficient. And we also talk about ZKML from the perspective of an application and use cases. In this podcast, we move from more software to hardware. So how hardware makes all these ZK things more seamless and democratized? Welcome our guest, Omer Miles, the co-founder and CEO of Ingonyama. And also we have a co-host today to help me dive deep into some questions which I might neglect. My friend Miles, welcome. Omer, would you like to share your personal background and what you are doing right now, and anything you'd like to let us know?
Sure. So thank you for inviting me, first of all. My background is hardcore technical background, and at some point I turned into an entrepreneur. So this is my second company, Ingonyama, that is dealing with cryptography and infrastructure. And before that, I was focused more on software and I guess a bit more into the cryptography, and now it's more into the math. In both cases, main market focus is the blockchain Web3 industry, and I mean, previously it was about making it accessible to the first billion people. Now it's about expanding the boundaries of Web3 and basically decentralize everything using cryptography and making these tools, which are like really amazing, available to anyone outside of the space. Kind of like, as I said, just making sure that we are able to use them, anyone, anywhere. Yeah, I mean, from academic background, I was a physicist and engineer, electrical engineer, and eventually turned into computer science and cryptography at the time of my PhD. And yeah, and as I said, like being in the space for how much time is it now? At least since Ethereum started, that's kind of like my main milestone that I remember. So I have a good recollection for when this happened.
Thank you. And Miles for helping me ask some more interesting questions. So could you introduce yourself?
Cool, yeah. Hi, welcome. I'm Miles, the co-host for today's podcast. Thanks to Francie for the invitation. Firstly, I will briefly introduce myself. I'm currently a postgraduate student in ZK research and also an intern at China for ZK. Recently, as I have been working on optimization of underlying ZK primitives such as MSM, elliptic curve, finite field operations. And I came across Ingo's impressive achievements in ZK hardware acceleration while learning from Ingonyama and after communicating with Alan. I'm now to serve as a Chinese ambassador for Ingonyama. And finally, thanks to the Ingonyama team, and once again, welcome, Omer.
Okay, thank you. So what is Ingonyama and what is the primary purpose or mission of your company? Omer, could you give us a very brief introduction?
So first and foremost, we are a semiconductor company. Now the thing to know about that is that usually these companies, work in long cycles. It takes time to establish such a type of a company, but at least you need to start somewhere, and we are very young. We started not long ago, but that's the DNA, right? That's the type of engineering and culture that we have here. And that's also part of our thinking. So if I'm trying to put aside for a moment where the market or the industry, what's the status of ZK today, and trying to just like project into the future and where we want to be. We want to be like the NVIDIA for cryptography. Yeah, I guess that's the best analogy in today's term. Basically, it's having, in terms of vision, is having access to zero knowledge from any device. It can be your computer, IoT, mobile phone, data center, and even like more broadly, like there are other cryptographic primitives that might be useful to remove trust or to increase privacy, which are two main things that we aim to improve, and again make it like, well, democratize the access to those. And yeah, I mean, it's a long road. So therefore, when I guess for many of or most of the time I'm going to spend here talking about the company, it's going to sound like we do quite a lot of things which are not really in that like direction or focus. But yeah, overall, there is this kind of like long-term roadmap that should lead to that, but we need to take into account that eventually we need to go with the market. I mean, part of our philosophy is that it wouldn't help for me to just have an ASIC in the market today. It will not serve any purpose. We need to have this ASIC when the market and the industry is mature enough to actually take advantage of it. And there's education already, and everybody can actually benefit and understand what it is doing. So that's kind of how I see things. Like there is the long-term idea, which everything should eventually align to, but there are many other different milestones along the way to get us there.
Yeah. So basically, what is Ingonyama doing is like help us get to the point where we can do really trustless computation, ZK computation. While we look at the traditional internet industry or any groundbreaking technology, we see that like software, algorithm, hardware are often integrated and optimized to create a cool new ecosystem. So in general, why do we need hardware to accelerate in this ZKP computation? Otherwise, we may not like unleash the potential of this magical ZK. Okay,
yeah, that's a fantastic question. So first, I guess as a general rule in history, usually for a technology to break into mainstream and become successful, you need software, hardware, and algorithms. If you look at AI today, which is really more mature than us, you can see that the way that we even measure, or like the way that we talk about AI is in terms of system. Like we start from the hardware. Like you need to have NVIDIA GPU, and you measure performance on that GPU, and you know how to basically play all of like AI models on that GPU, and therefore you need to build software for that, and obviously to improve and optimize, you need more algorithms. Now, the fact that eventually this is what we need doesn't mean that this is how it's starting, right? So obviously with many of these technologies like zero knowledge, it starts with algorithms. So someone in academia 40 years ago, like very actually someone managed to come up with this idea, and from that point algorithms kept improving and kind of like showing us that the complexity can be lower and lower until the point where we can understand what is the trade-off that we want to make when we actually approach the industry and try to make this like first breakthrough in production system. Now, the first thing you do is you implement it like naively on whatever hardware you have, and the most accessible one is CPU. But CPU is meant for general purpose computation, right? So most cryptography is finite field arithmetic, which is a different kind of a beast. It's like simply, there is better things. It's not like you cannot run it on CPU, but you can do much better if you run it on hardware that can actually was built and designed to support this type of mathematics, right? So it means that, like in terms of where the industry is that we started to use this like software based on CPU, but now we already been able using like competitions like ZPrize and companies like my company and others, been able to observe and see and measure results on different types of hardware, so that we can have this like better understanding of, okay, so hardware can actually get you more performance. I mean, so that's maybe more of like to the technical side, but I guess part of the question here is also, why do we even need fast ZKPs? I mean, why cannot I have, or it's not just fast, it's also efficient, like you want them to be cheap. And it connects in a way to what I said before, which is about removing trust. Like in essence, technologies like zero knowledge proofs, other privacy enhancing technologies are aimed to be used by end users, by us, right? To make statements without centralized parties and to hold privacy. And for that, you want to be able to achieve the same user experience that you have also with Web 2 and the internet. So if I need to make now, let's say, a transaction, and I want it to be private, but it's going to cost me a lot of money, or it's going to take me a lot of time, or it will require some very, complex hardware and like setup. I don't know. It's something that I'll probably avoid doing. So you want, or part of the reason we use hardware is to bring these requirements to very like similar levels to what we have today with Web 2.
And so is hardware always the backbone of blockchain? And what makes ZKP computation different from the past POW mining?
So I don't know about statement like hardware is always at the backbone of blockchain. I'm trying to, stick with what I understand, like in better terms, which is cryptography. And at least for this type of cryptography, it's very clear that there's like bottleneck or bottlenecks, and some of them are compute bottlenecks, some of them are other bottlenecks, like can be memory network, but they can be solved using hardware. Like this is the extension of Moore's law. In a way, if we want to keep improving the technology, we need at some point to align with this type of like Moore's law and start improving the hardware to be able to run ZKPs more efficiently. Now, you can actually use zero knowledge proofs as a way of doing proof of work. There are actually papers that are showing that, and there were even experiments with some blockchains like Alio that done something similar. So in terms of exploration, this is something, if I were a mining company, and some of them like both like not Bitcoin, but both like, a ton of like GPUs for Ethereum, for example, I would explore, and they are most welcome to also contact us, would explore ways in which you can utilize these farms, data centers of GPUs and other type of hardware. Again, not Bitcoin miners, because they are like very specific, but to see what you can do already today in terms of ZKPs. And there's going to be probably a use case, and it might also be like early adopters, and maybe the first use case for zero knowledge proof would come from this type of like consensus and proof of work. So it's something that can also help you push the technology, right? If there's this competition and different teams want to kind of like push it, like what we did with Bitcoin, so eventually it will lead to some even better hardware design. But I guess if you think about it like more broadly, zero knowledge proof do not stop there. Like it can be seen as many other things. Like for example, there might be a big market around just adding ZKPs as a feature in AI products, right? Imagine an AI company that now wants to have this kind of like verifiability using zero knowledge proof. It can be another feature that would require you to either reuse your hardware or buy new hardware. And it might also have requirements that we are not met today with AI data centers and hardware. So we might see in the future some different types of data centers that are tailored for ZKPs. And I mean, part of what we do is we try to enable this type of, first just to think and ideate about these data centers and how they would look like, and also how they can be put into good use by again end users, right? So how can they be accessible to anyone in a trustless manner? So yeah, I mean, I guess the short answer is that there are similarities. Like you can probably like replace proof of work with ZKPs, but ZKPs are way bigger than that in their potential.
Okay, so yeah, I heard that you mentioned AI and some data centers. So like beyond blockchain, will we have the chance to see the points that we really can adopt ZK in everything? Do you feel there is a huge demand for this? Yeah, and speaking of this, I just thought of a use case that I'd like to expand upon it. That is a proof of solvency for centralized exchange. So for the traditional banking system, like, because at some point there those centralized exchanges do not generate proof frequently. One reason is that to maintain this proving works is so expensive, and sometimes to verify a proof is not that user friendly. So given these two reasons, like centralized exchanges are not willing to generate a proof in real time, and users are hard to verify proofs. Is it a good niche for ZK hardware industry? Yeah, I'd love to get your thoughts on this. Yeah, or any use cases you would like to share.
Okay, so just before exploring use cases, just we need to say that here the question is not necessarily about hardware, but more about the necessity of ZKP and I would like even say
Yes.
privacy technologies in general. And I mean, we've been doing that in the company since very early on, trying to explore different verticals inside and outside the space. Because basically, I mean, what we can do is we can take any type of hardware and run zero knowledge proofs on that hardware and basically bring you the full solution. So when you think about it from that lens, it allowed us to have conversations with different types of like industries. So just to give an example, like a very far end of the spectrum example, we went into cameras and like IoT industry. So you have some IoTs that are meant for like surveillance, like you want to monitor some perimeter. And usually or like one way to do it is by collecting data from data points, like from these IoT devices, doing some processing on the device and then sending it to some centralized server. Obviously, there is an issue here because you are sending a lot of data, which is basically noise or nothing to this data center, to decentralized like server, which basically makes you pay quite a lot of money on that in terms of the storage that it requires. Now, still, you do need to have this like logic running in the data center because no other way. So you do need to get this data. But what if we can have this like zero knowledge happening at the edge, basically proving, let's say it's running some machine learning model saying that like detecting events. So what if we're going to run this like ZK at the edge, basically showing that there was nothing happening for like some period of time. So then instead of sending all the raw data, you just send a proof, which, as you know, is very, very small, a proof that nothing happened. It's like mathematical proof, nothing happened during that time. I mean, it's something that we actually explored with companies building this type of like cameras and chips doing machine learning on IoT cameras, and they were interested. I mean, eventually, when this technology would mature, this can definitely be viable for them. And as you can see, this allows you to bottom line to save money, which is why I use this example, because not often there's the ideas, yeah, we want to have verifiable, we want to remove like centralized parties and so on. But here I'm basically saying I'm going to save you the cost of doing all this storage and processing by doing something on the IoT side, which will compress a lot of data into small proof. So I think that necessity would probably and saving money would probably be one of the leading factors in how this technology is going to get adopted. I I can give you another example that like is similar but different. Now there's a war. When we now record it, there's a war between Israel and Gaza, and I think people realize that the actual war is psychological war. Is like, how do you impact like the public opinion into which side is winning and get to kind of like continue the war or like get criticized and so on. It becomes more and more significant. We've seen it with the Ukraine and Russia war. So where is ZKP? I think that in future wars, mathematical proofs like zero knowledge proofs are going to be crucial, because you want the sensors to be able to prove that they send data which is authentic, right? So then when I try to make a claim about something that happened or did not happen, now I have a way to back it up mathematically. Yeah, this is an image. It was taken from that sensor. It was not altered. You now see it, or a movie, right? So again, here ZKP would emerge out of necessity, because eventually war would dictate that this is like a weapon in a way that would help you defend yourself in a war. There are many other verticals that we've covered in different blog posts along since we started the company, around gaming and metaverse and AI. There are a few others in the pipeline around banking and identity and ads and privacy with ads and like traffic in the internet. So basically, we can just talk on and on the topic of use cases, but I want to stop just here. And one last sentence is, as you can notice, all of this, or the two examples that I gave, obviously involve hardware. So you cannot escape the fact that eventually ZKP needs to run on some hardware, which is not what we, oh yeah, let me just like, I don't know, take Arcworks, run it on my CPU, and that's fine. Something is going to be running on like some different type of hardware, which eventually we need to guide. Like that's part of what we do, try to guide to which hardware is better, more suitable. How do we develop hardware that would support this type of computation and make it like a feasible use case?
Yeah, so echo with what you were saying, that I just remembered that one researcher in Ethereum Foundation, he once upon a time he just said like ZK will help the peace of the world. Like someone doing researching in ZK may win the Nobel Peace Prize. Yeah, I think it's really amazing that we may do some really stuff with ZK. So upon your background, like we are talking about use case, and actually now it's more and more academic like cryptography academics are moving forward from researcher to the real producing industry. How do you see this phenomena?
So I think there's like no really other way, and maybe I didn't look that deep into that on how other technologies eventually emerged from academia and very kind of like theoretical aspects to become mature enough and penetrate and eventually scale in the industry. I know that from my experience, like it worked for me before, like in previous life, like my previous company, I took multi-party computation, which is another like privacy enhancing technology. And I've seen, I believe I had some contribution in that, seeing this technology mature enough and becoming like a standard. And I think that, I guess that it's by chance for me, like I was just like at the right place, or like focused on my passion, what was my passion, but eventually led me to be in a very good position to actually help this transition. But I think that's how you can do it. Like you have to be extremely, and all of the companies, by the way, doing ZK hardware, they have like extreme deep tech backgrounds for founders, many of the first members of the team. You need to have this like strong leg in theory, in research, and also you need to have this mentality of building things, launching, deploying, testing, iterating. That's critical. And I don't know, for me at least, my entire career, that was what I was doing. Like I was never doing research. None of my papers is like full theory paper. I was never doing research without implementation, and usually also like with open source implementation. So it was always important for me to see who's there on the other end. Most of the research questions that I was exploring came actually from needs and pains that you have in the real world. That's kind of like what drive most of my work as a researcher. And I think that now when I build a team, or when we are building it in that image. So we are bringing these members, these PhDs that have or had quite a lot of experience in actually building products, real-world systems, never doing research standalone. Like, it is important, but if you bring someone like this, you also need to make sure he's like connected with the most, the more with the engineers in a very tight way, and there are ways to do that. But eventually you grow as a company, as a team, so you have this kind of like culture around you, which basically says you do the research, but you know that like when you are guided by a very specific research question, you must kind of like describe exactly how is it that you're going to eventually go forward with it into real world. Otherwise, it makes less sense. Yeah, so I mean, that's it's probably not a very objective answer, but kind of like how I think we evolved as a company.
So building a company, it needs a bunch of work, much research and efforts that you may try a lot of times. So what is Ingonyama doing right now, and what you guys are specifically focusing on? So before we continue, I'd like to share an observation that I've noticed that many developers are intrigued by ZK proofs, but the complexity of the underlying mathematical theories and algorithms can be overwhelming, so making it challenging to start building. So I'm just wondering, is there a more straightforward approach for them to generate a proof? This might be connected to what Ingonyama is working on.
Yeah, good question. I think that, and I'm completely biased here, but I do think that our industry, like almost all of it, is now focused on building what we call middleware. And it might sound like a bad thing, like where are the applications, but also it's very important and critical to have and build tools that are accessible for developers and allow them to, as you say, kind of like remove complexities and have this like user and developer experience, which is very intuitive, and you don't need to overthink about like the underlying math and stuff like this. Obviously, you need to expose that as well, but this is kind of like, let's say, for power users, for researchers, for, I don't know, some people that want like new protocols and so on. But ideally, most developers would want to have this like ZKP at the touch, like at the one-click ZKP deployment, something like this, or close to that. So I see quite a lot of efforts around that, and many also just going in that direction, like Starkware open sourcing their prover. One good example of, it's not necessarily making it easy for others, but now it opens up for many dev teams to build on top and kind of like build the tooling that would allow others to enjoy this like a very sophisticated prover. Aztec doing this now, sandbox, and also DSLs, like high-level language for writing ZKPs. I mean, this stuff become more and more easy with time, and it's very nice to see. I guess that our focus is in a way in the same line with all of that, meaning that we needed some time to understand where, as an industry, we exactly stand in terms of hardware adoption, and it was very clear that today, when a new team of developers is building a protocol, usually they take something like an existing framework and then they start tweaking it and optimize algorithms, which still there's a lot of room to do, and optimize on software, but they're still missing this part of just running on the right hardware. It's not even like optimizing. It's just like, imagine like, writing an AI paper today, publishing it, and using CPU for your AI benchmark and performance. You cannot imagine it, like no one does it. So we need to do the same with ZK. So right now, I think at this point in time, it's just about getting this like standardization, having a good way to even measure, like, what does it mean? Like, I see even hardware companies making these mistakes. How do I compare between the different like appliances solutions? So having this, like, best practices in place, allowing teams to deploy on the right hardware, that's our main focus at the moment.
So can you introduce two primary solutions for ZKP acceleration and what's the path that Ingonyama takes?
So I would say that today we still do not have ASICs for zero knowledge proof. Now, we've mentioned mining proof of work before, and by kind of wrapping, or this is going to be maybe one type of an ASIC eventually, which is going to be specific for an algorithm and some very specific use case, and would not be able to do much more than that, but would do the exact algorithm very efficiently. We don't have yet candidates even for like such specific algorithms like what we have with Bitcoin, for example. And that approach is probably, there are companies in the world that are really good, like in terms of taking an algorithm and making and doing tape out in an ASIC and packaging it and so on. So, eventually this is going to be probably one type of business. What we do have today is we have access to quite a lot of different hardware devices that for some of them, we already start to understand how they can work with zero knowledge proofs. So CPU obviously was like the most battle tested, but what happens when you try to take ZKPs into the cloud? So today with cloud instances, you have all different like setups and configurations. Can ZKP run efficiently in the cloud? So that's one path and solution that you might explore. And we talk with some cloud providers trying to better optimize the type of instances that can actually support ZKPs, like, I don't know, running scroll. Like today, running scroll in, let's say, AWS is challenging, okay? It's not going to actually produce you the best results. But we do want eventually to get it accessible to anyone, so having it on a cloud instance might be a good solution. Same goes, by the way, with like data centers that have this, like, can be configured in different ways, and it's still like a good question what exactly should be this type of configuration. But going more into the chip level, obviously the two most accessible categories is GPUs and FPGAs, and here we do start to have a sense of how they work with. So at least in my company, we started with building IP for hardware, for FPGAs, for ASICs, and start to play with how MSM, entity, all of these problems actually play out on hardware, which is like one important insight, and eventually would lead into design that we think would be relevant for a variety of ZK use cases. Like when we started, we thought, okay, just like put an MSM, put an entity on like IPs in a chip, and maybe some hash function, and you should be kind of like covered in many ways. But that's not good enough. So we've changed our design into like basically building the GPU ZK again. Like GPU is like more confined field elements and such. So we call it a ZPU. Like we have this concept of a ZPU, which eventually will be able to be programmable, just like when you program GPU today, but would be more optimized for ZK and other type of cryptography. So that's one type of exploration and solutions. There's still much more room to explore, right? So ideally, you want to run the entire ZK proof end-to-end hardware, and that's something the ZPU would eventually support. But what about FPGAs today? What about the companies building FPGAs? I guess same goes for GPU. So we are also exploring GPUs running snarks, starks, some kind of like hybrid solutions. What happens when you want to run it like on your Mac and the GPU you have in your Mac? What happens when you want to run it in browser, right, in mobile? So there's quite a lot of hardware open questions here yet, and directions to go. And we're somewhere on this kind of like spectrum trying to find what's going to work best for most of the use cases today and support these companies building ZKPs.
Yeah, so like as we discussed above, we want to make sure that the ZK applies developers can pay more attention to building like applications. So tools like ICICLE, the thing you might want to say that you are working on is right there what we need. And Omer, can you explain this as brief as you can? What is this library used for, and what can like developers can use it? Like is it a out of box toolkit or something like that?
So ICICLE is very simple to explain. Basically, today, let's say you have your own like ZK based product and it is running on CPU. You have your customer base, your users, and eventually you're going to have a pain of scale. That's again like very specific to where we are today in the industry. You want to make it faster, you want to make it like the ZK more power efficient, and so on. You need to move to hardware. You need to basically let go of the CPU and start running on specific hardware. ICICLE today supports NVIDIA GPUs, and it allows you as a developer, either if you already have an existing ZK protocol working, to port it into GPU. So you basically move one part at a time to run on the GPU and not just on the CPU until you can run everything on the GPU, resulting in immediate performance boost. And it eventually would also allow you to work with other types of hardware, but today it's just like this GPU, which is very accessible and easy to program. And I mean, also if you are a researcher and you just want to, implement, as I said, like with the AI on CPU paper, which would not happen. Again, here I do expect that papers would start to build on hardware and to benchmark on hardware. So that's kind of like the way forward. You can take components from ICICLE, combine them in a way like Legos and build a new protocol out of that, and then benchmark it. And the API should be very intuitive and simple. Again, like meant for developers like with Rust, Go language, and so on, that should be like familiar with it without the hassle of, oh, that's like under the hood what I need to accelerate and so on. So it should be very simple. Yeah, I mean, I can talk more about the roadmap for ICICLE if you want, but that's the basic idea of this library, aimed for like any developer that uses ZK and allows you to basically run on GPUs.
So currently, which ZK online primitive and elliptic curves does ICICLE support? It seems that it haven't supported the pasta curve yet.
Yeah, okay, that's very specific, and indeed, pasta curves are in the roadmap. Same goes for small field support, and many other things. So it actually kind of like a blue ocean. We started from supporting snarks in a sense, and even like before they're just supporting the primitives like MSM, NTT, hash function in a Merkle tree, like where we usually find like the main bottlenecks. But yeah, going forward, we are going to start supporting both like more primitives, Stark provers, more protocols, make the API better. I mean, for us, API is the most important part. There's also work on the algorithm level. So it starts even like lower than elliptic support. Modular multiplication is an area where, I mean, it's a very old area, like 40 years algorithms, and not much innovation can happen there. But even though, like, still, when you match this type of like algorithms with like hardware, like cutting edge hardware, there are some things you can do to shave off like some percentage of performance, and because it's very low level, you benefit or you gain from it across like the board. Like everybody wins, all primitives, everyone using ICICLE wins. Then obviously we want to support more elliptic curves. and so on. So there's also finally the improvements on the CUDA level, right? So GPU, NVIDIA GPU usually like programmed in CUDA, and like there are some lower level stuff, and there are some techniques, I don't know, like graphs that we haven't implemented yet, and so on. So yeah, there's also just improving the on the CUDA side, like of engineering things.
Yeah, that's cool. And I know the ICICLE also supports MSM like in G2, and I think it's very useful for some ZK snacks like Group 16.
Yeah, we do support MSMs G1, G2. There's also this ECNTT, which we once tried to, we identified as part of Alio, and then we've seen that it's like, it's very common to have this like entity with EC points. Like for example, like when we released ICICLE for the first time, we also released an application. Eventually, it's an open source library. Developers can build any application they want, but we wanted to show, one example. So we used dunk-sharding, Ethereum scaling solution, and we extensively used this like ECNTT thing with that, which eventually led to a very nice and promising performance boost. So yeah, there are some unique things. Like, right now, for example, we are looking into sum checks. Like no one done sum check on GPU. And if you think about it standalone, not sure if it even makes sense. But one thing that is like, I don't know, an open question for me is, can we have a hardware efficient sum check and maybe an isomorphism to that from other type of sum checks, which are very popular today? And the other thing is, sometimes even if it's not like optimal or faster than CPU, if it saves you the round trip, I need to go back to the CPU to do the sum check, then to go back to the GPU, to the hardware, and you lose a lot of time on this like round trip. So even if you just like do it in the GPU, not efficiently, but still it saves you the round time, often it's like improves the overall performance of the system.
Yeah, so I had a more general question for you. So one part of your partners or customers you are focusing right now is obviously on the zkRollup scaling side, and gradually some zkRollups are launching their mainnet. And what would Ingonyama prepare for it? Or more specific, Scroll just launched their mainnet a few days ago, so they will have a proven network. And how will Ingonyama prepare for this? And how will ICICLE continue to evolve and in which direction?
Okay, great. So zkRollups have been one of our like main focus points for a long time. And part of that, even it goes to, if you look at our investors, we have Polygon, Skoll, Starkware, ZK as investors, and obviously we are also in very good terms and good friends with Tyco and other L2s. Therefore, we've been tracking and trying to figure out or answer these questions ourselves for quite some time. And zkRollups are often like differ from one another, but there are also many similarities. So we do have projects with most of them in different level of maturity. Skoll, as you mentioned, launched mainnet. Now you need to separate between launching mainnet and launching an incentivized and decentralized proven network. So today, proving in at least when we record it, proving with Skoll is still centralized. However, it is something we are also participating with, right? Like, so we do work with them on understanding better the performance that their own native prover provides, and understanding how much we differentiate from that. Because we started to develop our own Skoll prover some time ago, and we have some promising results. It might be good if it's just a different approach, not even like different in performance, but just a different approach with different type of like setup can make it more accessible to different users. So that's one approach. Just by releasing our prover would allow maybe to extend the who can actually use and run Skoll provers. We might also have some ideas around like prover optimization that either Sproul can use in their open source, eventually open source prover, or I don't know, we can just like deploy with some of our partners, right? Like mining companies, I know are interested, some data centers are interested, mining pools, I even like, you know, we've been in touch with you. So we need to see how it evolves and who are the stakeholders and are actually interested in participating in this network, eventually understand their setup requirement, right? Like, because I can build a solution, an algorithm, but it will be not accessible by anyone because like too much, like the requirements are too high. Or I can build something that would actually work with the hardware that people that wants to participate in the network actually have. So that's kind of like our approach. We first partner with people that has access to hardware, and at this point they are, you know, more of like idealists that want to participate in the network, and we do our best to support them, right, by whatever means necessary, all the way from like just tailor solutions to their hardware to open source and contribute to eventually the improvement of the prover efficiency overall.
Yeah, so actually, open source is crucial to onboard developers, and education is so as education. So just take NVIDIA as an example. What they did to pave their role for their CUDA ecosystem is huge. So, right? So cooperate with professors and researcher teams at university is how they did it. And I think is kind of become CUDA is kind of become the standard architecture for GPU clusters. Yeah, I'd love to know what's Ingonyama's strategy for this like developer ecosystem growth.
Okay, so it's, I mean, as you pointed out, NVIDIA done something amazing with their approach and building CUDA and making it accessible and used by people from academia. I wish we can just play the same playbook, like use the same playbook and run the same. Obviously, it's not going to be that simple, but we definitely try to learn from the best and you know, copy what we can in terms of education and practices that work. Right now, I think going open source is an important step. Like, I think it's kind of like lowering the barrier. It allows people to review the work, to use it for whatever they want. And it's not just open source, it's like permissive license. Like we don't take any IP in that. Like if you are in academia now, first I encourage you to reach out to us and collaborate. But obviously you can just like use this ICICLE and other tools we've released to explore, to do research in Zeek acceleration. That's important, kind of like enabling that. The other thing we do is that, you know, we try to be open and inviting as possible. So we want to have this ecosystem which is active and people feel free to ask questions. That's kind of like the DNA. I mean, I've worked on open source projects for many years now, and that's kind of like the DNA that I like, is that, you know, you have this project. It's not owned by anyone, but we do have some advantage in understanding this project and advising others and helping them. So eventually it's about helping communities, ecosystems on different parts of the map of ZK to just onboard and start to use these tools, these software tools. I know that hardware would come easily afterwards, because once you already use you know, like the CUDA equivalent of ZK, like stuff that we try to build maybe, then changing into another hardware is relatively, I mean, if you change to another hardware that obeys the same software, it's definitely going to be an easy transition, and also can be economically viable in many ways, because you just like give someone a better hardware to use. So yeah, I mean, I hope that hardware would follow after software work. So we do put a lot of work into software education, making it accessible.
Yeah. Okay, thank you. And I think we can continue to talk, but now I think it's almost about time. So yeah, you as the co-founder and CEO of Ingonyama, why don't you just share your vision of Ingonyama as today's ending?
So one thing that I can share is that for us as a company, it's very important to not hold the technology close to us, or, you know, to be influenced by geopolitics and geography in general. we have investors from across the world. We have many investors. We have many companies, big companies that have a lot of stake in ZK that are working with us. And I think this is like part of eventually building a product that would help with, again, like getting this technology, like remove decentralization, remove centralized points, help privacy. I think this is the type of consensus that we need. This is the type of buy-in that we want, and I'm very happy to see it like plays out so far. And again, when it comes to a vision here, I mean, for me, it's super important that we'll continue this as, you know, kind of like a global effort and collaboration to push this front. I really believe in this mission, and I really think that like some of the examples I give, this technology can matter, can change. I mean, you said Nobel Prize. Not sure if I go that far, but
yes.
I mean, yeah, definitely it's something that would move the needle and would change how things are being done and would eliminate elements of corruption. And yeah, I mean, we just want to make it, to see it happen.
Yeah, thank you. Awesome, appreciate, and thank you for coming here. Yeah, so goodbye.
Bye-bye.